Thanks. Yes, I am from Erste Group Bank. Thanks for inviting me here, and good afternoon. So let's start. Today I will speak about the Erste Group quantum prototypes, which are EARThQuaKe, QuEST, and MoSAIQ. But before doing that, I'll spend some time to speak about our team, the Quant team. The lining did not come as expected, and to stress what our goals are. Here we go. So in the top left, you see the girls and the lucky boy with the girls. Then you see the other boys, poor boys, working in the table and doing stuff, also with the girls, of course, sometimes. Then you see our boss, Mickey, in front of the IBM Quantum System 1. And then you see part of us in the top of the rock in New York at the IBM Quantum Summit. I said about goals, I think it's setting the right goals is the key to not overshoot and to deliver what you put up front to deliver. It's an important strategic point. So the first goal that we have is finding banking use cases. We are a bank, so we want to find use cases which can be tackled in quantum, either fully or partly, right? So we are not gonna use quantum for everything. I'm not gonna try to use quantum for projecting this image on the screen. That's not very good for quantum. So the idea would be to screen and to find those use cases which you can really tackle in quantum, which is an exercise by itself. After you did that, well, you need to concretely and effectively put those use cases down and trim them and tailor them and build a quantum circuit for those use cases. This is not easy, and that's normally this is the step where you are seeing which use cases are really can be really tackled by quantum, which ones not. And after you do this, use please not toy data, because toy data is easy, but use also real data, because that's when you are using real data and use the real processing, you see, and you put your hands dirty on the processing, then you see when things are working, when things are not working. So these three are for framing it. Then what we aim at is not to obtain a quantum advantage, not now, it's not the time. We want to have results which are anyway comparable with our classical computation, right? So what we want to have eventually is having a classical solution on the left-hand side, which is running anyhow. And then we want to have the quantum solution which runs side by side, which delivers comparable results. So, and once you get that, then you need to have also a perspective then that as soon as the quantum machines will get better and better, then you can already time tag when your quantum solution will bring business value. So I said it before, but I will repeat it now. I think it's important again in the goal strategy. We don't need to get quantum advantage now. It would be nice to have if you have, but we need to have a good overview on when this can be achieved, and we need to build stuff on the real framework, not on toy data, please. Setting up our goals, so we know upfront what I am aiming at. So I'm gonna speak about our 3 quantum solutions. They are running, they are prototypes. Two of them are in the production environment. One of them will be soon in the production environment. They got fancy names, and will, as it's normal for quantum, right? It is a long research for the name of the solution. So first we speak about EARThQuaKe. So you are going to ask what is EARThQuaKe about. So EARThQuaKe is emission allocation realized through quantum kernel. If you read just the uppercase letters, you'll get EARThQuaKe. That's the goal. And what is it about? Well, emission allocation, you already understand, is something greenish with green stuff for banking. It is indeed the case. So as a bank, strangely enough, we are more and more pushed by regulators, by European Banking Authority especially, to screen our customers and to see how green they are. Why? Because if you are asking for money, if you're asking me for money and the bank, and you're the customer, to buy a house, your house, you have all the rights to buy a house. But then as long as you don't give me back the whole money, you are buying a house with my money. So if the house is polluting the environment considerably, then I will be responsible for it. Similarly to you, I don't know, you want to build a factory, and then the factory is polluting the environment like crazy, and maybe you go even default after 2 months. So your factory comes to me, then I am the bank having a factory. I don't know what it is doing, and it's polluting the environment, right? So it's not a nice thing. Moreover, it's a general push from the whole ecosystem to you move the economy by moving banks, right? If the bank is giving money to green people, then more green will come to society. So the idea is good upfront. So we are doing this, and well, the why I already highlighted. And how are we doing this? There is an in-house built solution called carbon footprint calculation, which calculates the carbon footprint of Erste Bank by screening the customers and the usage of the customer, what they do with our money, what kind of factories they have, which kind of pollution to the environment they with their collaterals, with their factory are responsible for. So the CFC solution, the carbon footprint calculation solution, is made of several steps. Is a complicated solution, but one of the layers, the fourth layer, is called emission allocation. And what does it mean? Well, it means that I have buildings and I have exposures, which is money that I gave to you, for example, or collaterals, anyways. And then I want to know what the linkage between the emission that your building is giving to the environment. I want to have the linkage to which money, which amount of money, which pound of money is responsible for it. So, and this linkage is a coverage problem, so to say, which is trivial if you have a one-to-one relation, right? Which is it is actually the majority. The majority of the case, I give you money for this one, for this building, for example. So the whole amount of money is related to the building. So the emission of this building will be the emission of this money. But you can imagine if I have large customers, when they have many deals with us, many exposures, and they pledge as collaterals several hundreds of houses, cars, whatever, then the linkage is not straightforward. So we need an optimization method to find which emission goes into which money I give to them for. And this is an optimization problem in principle, because we want to find the best match with the minimum emission. So sounds like something that Quantum can solve, a coverage problem, optimization. So we heard some optimization thing that Quantum is good at. So bang, first goal is satisfied. We found a banking use case where Quantum can be usefully applied. So we go forward. How do we do this? As mentioned before, we have a classical optimizer, which is in this case built in SAS, fine, which is the production line. Don't touch this. God save us, otherwise the business comes with a knife at the back. Don't try. But we carefully put on the same place, on the same platform, other two optimizers. One is what we call full quantum optimizer. One is what we call quantum inspired optimizer. So what is what? So a full quantum optimizer is rephrasing the optimization problems into quantum terms and solving it into IBM full quantum machines backends. The quantum inspired is getting the same quantum formatted problems and solving it with classical optimizers. And what we are aiming at is building a monitoring tool which tells us what is doing what, right? So if the classical optimizer is doing a good job or not, if the full quantum is giving quantum supremacy or not, and so on. So we aim at the monitoring tool. The monitoring tool got the name seismometer because it's earthquake, right? So we are monitoring the earthquakes here in this particular case. So let's start with the full quantum optimizer and see where we get to. So we are working with IBM, so IBM Quantum, which we thank, and we are running in their machines, which are Sherbrooke, Torino, and anything. You can just choose the one you like the most, which was also Kyoto, and I star marked it because, of course, we are running green topics. So of course I want to run it on IBM Kyoto, right? Because who doesn't know the Kyoto Protocol, the treaty of the 90s for reducing the emission worldwide. Yeah. So it would be nice if IBM gave me free shots to run on Kyoto because of the topic, but that's not the case. So we were running, and we did several runs, like you can see. So on the left-hand side, you see the qubits required for the optimization that we set it up. In the middle, you see the problem side. So it's going from few choices. So this is the optimization choices, the coverage choices that you are covering, that you are able to deal with. And you see that. And on the right-hand side, you see the accuracy. The accuracy is measured comparing the full quantum with the quantum-inspired optimizer in this particular case. So because for these things, the quantum optimizer inspired can deliver 100% accuracy. So the full quantum is compared to that. And you see that the accuracy is going down. Actually, we were quite happy to see 100% of accuracy, or even 65% of accuracy for 40, 80 qubits. So it's quite good, I would say. So the noise is kept to a good level. But of course, when we are shooting 111 qubits and the search space is larger, then the accuracy goes down to 4%. And I put down there 400 qubit quantum business value, where we would maybe need it, where we would find business value, because when I run the optimizer in this regime takes hours. So if to deliver the result I want. So if the quantum can do this in seconds or in minutes, then it would deliver some value. But we are not yet there, because for that I would need 400 qubits roughly, and roughly 100% of accuracy. But I think we are getting there. 2 years ago, we were far away from this picture. Okay, bang, 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 bang. We got 4 scopes fulfilled, right? We concretely built that use case into a framework. We ran it not only on toy data but on real data. This is real stuff. You see it's piled up with the classical optimizer. We got results that make sense. We even tabled the accuracy, and we got a perspective on when this will get to the business value. Quite happy. Going forward with the quantum-inspired optimizer, this is easier because it can be run on a classical machine. So now it's up on the server, which runs 24/7. No jokes. It's in the processing line, and that's what it delivers. Now we can feed it with a small amount of data, because still it's consuming a lot of power. The IT complained to me that I'm using too much CPU for that. But, so you already see that we get actually the classical optimizer gets 14, gets slightly less than the quantum inspired, and in the future we plan to extend the usability of the inspired to get more coverage, so 100% coverage, which would result in lower emission. So it's and we get there. We fulfill 2 more tasks, which is getting the solution run side by side and get even business value today. In this case, is emission allocation, more coverage and less emissions. Let's go to the next one, QuEST. What is QuEST? QuEST is Quantum Elimination and Selectron Transformer. Again, if you read the uppercase letter, you get QuEST. What is it about? Well, in the bank, like in many other institutions, we have data science team. They want to build models. In our case, for, I don't know, product recommendation, for example. And this is made of several steps. As you see on the right-hand side, very simplified. One of the steps is feature selection, and we want to do this in quantum. And we already heard a talk from Kipo, who is doing very similar things than us. It was totally independent building. And well, this is actually useful, because when you have several thousands of features from the customer, you don't want to use all of them to build a model. You want to select few of them, and the normal classical methods to do this take time. So what is it now? So we built this QuEST, as you can see. This is the pool of data science toolkit. It's a pool of tools that a data scientist comes and can select to put in his or her pipeline to build the model with. So what happens is that one data scientist comes and chooses whatever he wishes, and he can now choose, whoever comes, our quantum inspired or full quantum solutions for QuEST. So it's already in the official pool of Erste Group Bank, and we ran it on propensity to buy model, and we got this stuff. This time we did not run carefully on different snapshots. These results are very fresh. So we were running with more or less the same space search, but on different data sets, and we got an accuracy of about 50 to 60%, which were quite good. Again, also this is the full quantum versus quantum inspired accuracy. Next, MoSAIQ. MoSAIQ also got a fancy name. We heard that Candela has also a device called MoSAIQ. It's not the same. This is Monte Carlo simulation administered in quantum. I don't know what the Candela's MoSAIQ is for. What is well, Monte Carlo simulation is a topic typical for banks, right? Banks, Monte Carlo simulation. So what are we doing with Monte Carlo simulations? Well, Monte Carlo simulation look like what you see in the right hand side. The graph, you typically start from somewhere. It typically for us is a market price, could be, or an interest rate. In this case, it's 142 or 43. I don't know. It's 2-day, and then you don't know the future, right? You don't have the globe to predict the future. So what you can do is estimating the future, but estimating means you are building different trajectories which represent possible values for the futures, right? So what is interesting at the end line, at the end point, you can draw a probability distribution where all the lines are where the lines are more dense, then you are more comfortable that your ending price will be there. Where the lines are less dense, then you say, well, the price will not be there very probably. So you use this for estimation and for risk assessment, right? That's the idea of the Monte Carlo simulation. And we are doing this in quantum, and we build even a graphic unit interface, so which is doing this. It's made of several sections, which you see the main ones here. It is loading data. In this case, it was interest rates, and then you choose the model to fit the interest rate with. So the past. So in this case, BM stands for Boolean motion, and GBM stands for geometric Boolean motion. And then after you do this, you project this into the future, and you run the simulations. And you run the simulations on a simulator or on a real backend, like in this case, IBM Brisbane. And you get the results on the right-hand side. And you see that the CMC stands for classical Monte Carlo, because you can run for this schema here, also classical Monte Carlo. And on the left-hand side, you see quantum Monte Carlo, QMC. And as you can see, for the expected value, things quite match, because it's a linear quantity. For the variance, var, or value at risk, V at R, things are quadratic, so the estimation completely fails. This was a run of several weeks ago already, and things in the meantime improved anyhow. Yep, and I think it's everything I want to say, so I made it up. I thank you, the whole quant team, for this, of course. It's the work of everyone, and especially Tamim and Stefano, which are also here from the quantum team from Erste Group Bank. Thanks.
Thank you so much, Filippo. We're going to take a few questions. We have 2 minutes and a half. Who wants to ask a question? Come on. Nobody?
Very clear.
Huh? Very clear. Yeah, too clear. Yeah. Okay, I have a question. Can you formulate any of those 3 use cases as a graph problem?
Well, the coverage problem, yes. The coverage problem, maybe yes, because you can. It depends on which buildings are, or which collaterals are linked to which exposures. So Stefano, by the way, drew once a graph showing which collateral is linked with which exposure, showing with the lines what we can see. You know, this is to some extent yes. The Monte Carlo simulation, I don't think so. Yeah, the QuEST, I don't think so. The future selection, or at least I cannot envision it. Maybe.
Thank you. Any other question? Yeah.
Just a quick question regarding quantum inspired. Was it simulated annealing and stuff like that?
No, it was just running. You know, you write down your problem into quantum terms, meaning that you are rephrasing it into trotter steps, for example, into quantum evolution, and then instead of solving it with the quantum solver, you solve it with classical solvers like Gurobi or Cplex or classical stuff which solves optimization problems and the classical top-notch stuff. And then it takes short time for short things, but it takes up to days for big things. So that is not what is the classical solution doing. The classical solution is doing some approximations. So it's doing some heuristic methods which are fast for the bank and for the bank purposes are also okay, while the quantum inspired would do an exact solution. And that's why I was telling you that in that case it takes 1 day to do it, and in that case the quantum full would give some business value, because then it would take like 20 minutes or 40 minutes run.